Okay, let us do a few more approximations by using Taylor polynomials. The first example is an example that we already studied. The example of the function f being equal to square root of x. We calculated the third order Taylor polynomial with base point 4, and this is given by 2 plus 1/2 times x minus 4 minus 1 over 64 multiplied by x minus 4 squared plus 1 over 512 multiplied by x minus 4 to the power 3. And what I claimed is that if we plug in the value of 5 for this polynomial, then this should be a good enough approximation for the function value at 0.5, which is square root of 5. Now, what is this approximation? Well, we calculated the value of the polynomial, and this is equal to 2 plus 249 divided by 512. And we want to make sure that this is a good enough approximation. By Taylor's theorem, we know that this difference is less or equal to the maximum over all values y between the base point 4 and the point of interest 5 of one of the derivatives of our function f, and the derivative that we have to take is one higher than the order of the polynomial, so we have to look at the fourth derivative of the function square root, and this fourth derivative is equal to 15 over 16 multiplied by y to the minus 7 over 2, and of course we have to take absolute values, but this is a positive number, and we have to multiply this term by the difference between the point of interest and our base point to the power 4, again one higher than the order of the polynomial. Now, what is the maximum value of this function y to the power minus 7 over 2? Well, the power is negative, so we have seen earlier already that the function decreases. So the maximum value is taken for the smallest possible value of y, which is equal to 4. So this maximum value is equal to 15 over 16 multiplied by 4 to the power minus 7 over 2. And if we calculate that one, then and multiply by 1 over 4 factorial, which is equal to 1 over 24, then we get, what was it? 5 over 16,384, and this is lesser than 3.1 multiplied by 10 to the power minus 4. So it's already a good enough approximation. So 3 times 10 to the power minus 4 is not bad. So the last example that I'd like to consider is the following one, where we are asked to determine an approximation a of the number 65 to the power 1 over 3. So this could be typically a question that has to be solved when you plug in the value 65 over the power 1 over 3 into your calculator. And we want to have this approximation satisfy that the restriction that the difference between the approximation and the desired number has to be smaller than 0.0005. So, okay, now how do we solve it? Well, what is the function that plays a role here is just the function f of x equal to taking third root, so it's x to the power 1 over 3. Now, to be precise, let's already calculate the derivative. So the first derivative is 1 over 3 multiplied by x to the power 1 over 3 minus 1 is minus 2/3. The second derivative is, well, the power goes down, so we get minus 2 over 9 multiplied by x to the power minus 5 over 3. And, well, I think this suffices for the moment. What is our base point? What is a suitable base point? Well, if we look at 65 to the power 1 over 3, and it's very close to 64, and 64 to the power 1 over 3 is an easy number, is 4. So we are in good shape because 65 is close enough to 64, and the function value at 64 is a very nice number. So we take base point a is equal to 64. Of course we could have taken any base point, but probably the order of the approximation has to be increased in that case, so it's better to choose a clever one. And we try first to take the just a simple first order polynomial. So let's calculate the first order polynomial with base point 64. Now this is equal to the function value at 64 plus the first derivative at 64 multiplied by the difference of x and our base point 64. And if we compute that, then we get 4 plus 1 over 3, where is it, times 4 to the power minus 2/3. No, not 4, 64 to the power minus 2/3 multiplied by x minus 64, and this is equal to, well, 1 over 3 multiplied by 1 divided by 64 to the power 2/3, and it is easiest to first raise 64 to the power 1/3 and then take the square, and then we get the following thing: 4 plus 1/3, so 64 to the power 1/3 is 4, 4 squared is 16, so we get 4 plus 1 over 48 multiplied by x minus 64. Okay, so what we try as a guess for our approximation is the value of this polynomial, of this first order polynomial at 65. So this first order polynomial with base 64 evaluated at the point 65 is 4 plus 1 over 48 multiplied by 65 minus 64 is equal to 4 plus 1 over 48. Okay, now is this a good enough approximation? We check it and we compute the difference. At least we compute a bound on this difference. Of course, a bound doesn't, if the bound is bad, it doesn't mean that the approximation is bad. It's only that we cannot check whether it is bad or not. So the difference between these two is never larger than the maximum value over all possible values of y between the base point and the point of interest of the second derivative of our function multiplied by the difference between the point of interest and the base point squared divided by 2 factorial is 2. Now the second order derivative is this number over here, and again, so we take absolute sign so we can forget about the minus sign. We have a negative power of x, which is decreasing as x increases, so the maximum value of the second derivative is taken at the minimum value of y. So this maximum is less or equal to the value of the second derivative at 64 in absolute value, so we get 2/9 multiplied by 64 to the power minus 5 over 3. And if we calculate that, we get 1 over 64 to the power 1/3 and then to the power 5, and so we get what do we get? We get 4 to the power 5 is 2 to the power 10, and it's always easy to remind that 2 to the power 10 is 1024, and so we get 9 times that thing is 9216. And if we multiply by the coefficient that we have here, so we get 2 times 2 divided by 9216 divided by 2, so it's 1 over 9216, and this is, well, if you compute it, something like 0.0001, and this is clearly smaller than the required upper bound that we had to satisfy. So indeed, we conclude that in this case we were lucky. We can take our approximation equal to the value of the first order polynomial with base point 64 evaluated at 65, and we can stop our analysis now. If this bound would have been too large, then we would have to compute the second order polynomial, check whether the difference with the value obtained and the desired value is small enough. If yes, we are ready. If not, we have to increase the order of the polynomial, and so on.